Hello. Del, I'm back in. I think we're ready. Welcome everyone to the battery energy storage system provided by Commonwealth. I am Christy Vilmano. I am the Director of Engineering for Power Generation and Energy. And I have with me a team of 3 engineers who have significant experience in this area to talk to you about what we've learned over the last couple of years. So I have Jack McCormick, 10 years in electrical power. He's the active project manager on several of our battery projects that we have been working on over the last few years. We have Ian Hunt, who will talk to you about his experience in supervising our electrical system studies for these battery energy storage systems. And last but not least, Colleen Koncevich will give you her experience in protection and controls and some of the stuff that we've learned on dealing with microgrids. So I want to welcome you. If you have questions, if you can put them in the chat as we go, then that will be monitored by other people on the team, and we will try to address all of those at the end. So I thank you for joining, and we will follow this up with some information on an up and coming seminar that we will have next month. So Jack, go ahead and start.
Thank you, Christy. Hi all, and thanks for coming. My name is Jack McCormick, and I plan to start this webinar off with some high-level overview of what a BESS is. BESS is an energy storage system that can be many different types of batteries. However, for this presentation, I'm going to focus primarily on the chemical-based batteries. Just to mention some of the others quickly, one type is pumped hydro, where water is pumped to a basin or pond at a higher elevation when electric rates are favorable, and then allowed to flow back down to a lower pond, making electricity when electric rates are higher. Compressed air is another battery that operates in a similar fashion. Air is compressed when rates are low and allowed to expand to drive a turbine when rates are high. And flywheel is another battery where energy is stored in a spinning mass. The use of any of these batteries is simply, in one way or another, improve our electrical infrastructure. Batteries can be used at small scale, like storing energy for use in your cell phone, or as large scale to power a home or small community, even a campus or a utility scale, to support our nation's electrical distribution and transmission system. Excuse me. The largest chemical-based battery is around 1,200 megawatt hour. To put that into context, a battery that large could power your home for 100 years, or 1,200 homes for 1 year. So when I say chemical batteries, I'm really talking about 2 main technologies that are deployed today. They are lithium ion and flow. Lithium ion come in a handful of different chemical compositions, and depending on the use case that I'll get into later, certain compositions may be selected. Vanadium redox flow batteries are pump solution or a flow solution to manage the ion exchange. There are pros and cons to each. However, lithium ion generally wins this battle, at least today and what we see in the near term. One of the main reasons this is true is because of the energy density of lithium ion. Instead of the small battery in your cell phone, consider or picture yourself wearing a backpack all the time to have a flow battery in it. At a larger scale, if a lithium ion battery took up, say, the end zone of a football field, the same energy in a flow battery would take up a good portion of the rest of the football field. However, with that said, flow batteries are better at storing the energy. So if the intent is to use a battery once a week or once a month, although it takes up more space, you'll spend less on maintaining a charge on the battery. A couple other benefits to flow is that they are arguably safer, where they don't experience thermal runaway, and they generally have a longer useful life. Where can they go? Batteries can go anywhere. I'll mention some design considerations a little later, but the only real consideration is that they really should be as close as possible to the load. Top left has the battery co-located with wind and solar. This really could be anywhere. Top right has a system rooftop mounted. We just got to consider batteries are pretty heavy, so rooftop needs to be reinforced, and there's also some NFPA 855 requirements to consider, and really involving the authority having jurisdiction early is pretty key on a project like that. On the bottom left, this is a location off-grid. It would be kind of similar if you place panels on the roof of your house and installed a battery in the garage to store energy for later use, and then you experienced a utility outage. This picture appears to be like a non-grid tied application with battery and solar. On the bottom right, this is utility scale. It's not our project, but if I had to guess, roughly 10 megawatt, 20 megawatt hour system. That's just based on the number of containers present and overall space it's taking up, and just experience working with these batteries. This kind of brings me to a new point. Batteries get rated in power and hours, or energy. That's why you see under DeWalt drill a 5 amp hour battery. That's the rating on that battery. So when the drill draws 5 amps, the battery will run for an hour. It's really no different for a large scale. 1 megawatt hour battery can dispatch 1 megawatt for 1 hour. So with a rating of 5 megawatt, 10 megawatt hour, the system can dispatch 5 megawatts for 2 hours. There are also beginning of life ratings and end of life ratings, like your cell phone. When battery's brand new, it's awesome, but over time you start having to recharge over the course of the day, when previously you may have gotten through the whole day. And then there's also the battery's round trip efficiency, state of charge, charge rate, and they go on. Sizes. Mentioned a couple times now, but battery energy storage can really be at any scale. From a Commonwealth project scale, we'd be interested in any scale that'd be integrated into a commercial application or larger. But on the left here, we see the Tesla PV plus storage system, and that thing takes up about an 8 foot by 8 foot area on the wall of your garage with PV panels on the roof. This is likely a 300 kilowatt system that could power your home for 30 minutes, and then even longer if the sun was shining and the solar system was operating. Picture on the right is like, again, guessing, but somewhere around a 10 megawatt system, and that would take up like 150 by 150 foot area. The large 1200 megawatt system I mentioned earlier would be like a few acres of space. Major equipment. I don't know about you guys, but I lost the major equipment slide. There we go. Major equipment. So what are all the major pieces of equipment for a project to go around the loop? Left is a battery cell, or actually I'm showing 3 battery cells. The cells that are maybe the size of a briefcase are wired together within a rack. I'm showing 3, but usually the utility scale project, there's going to be 10 to 15 cells in a rack, and are overall the size of a small refrigerator. And then multiple racks are then connected together within the container or enclosure. The racks are then wired to the inverter converter. Go back. Inverter converter, power conversion system, or it's an inverter and converter. Because this process is a two-way street, the power conversion system has to do both. Charging and discharging, it's converting and inverting. Unlike solar, because power does not have to flow 2 directions. Only an inverter is needed to make the system work. From the PCS, the AC voltage is stepped up to whatever the distribution voltage is in the area. Commonly we see 12 to 35 kV, but definitely been involved in projects where we're connecting up to 345 kV. Then the step up transfer is then connected to switchgear. Switchgear is where a lot of protection and controls are enclosed. Breakers with sophisticated relays, they protect the BESS system from itself and the grid. And then from the switchgear, power flows to and from the grid. And then I'm kind of leaving out a lot of equipment like HVAC, aux power, utility interconnection, but you have to say they all serve really a major role. Use cases. So how are batteries being used today? There are a handful of common use cases and a few not so common, but still valuable. The first on the far left is educational. There are some that are testing the water, just kind of learning at a small scale before they go big into their infrastructure. I'll add that project I'm thinking of is also benefiting from the other use cases, but learning about the BESS at a small level was really their primary goal. Another use case is energy arbitrage. This use case is used for taking advantage of cheap electricity, usually at night and in the morning, to charge the battery, and then dispatching when electric rates are higher in the afternoon. This is a profit-producing use case, typically deployed by developers. Peak shaving is a similar concept. When the demand is high, some equipment in the overall electrical network might be slightly overloaded. So peak shaving with BESS near the load might prevent the case of an overload and on some pieces of equipment and overhead line, potentially. So some are using this specifically to push a substation major equipment replacement into the future, just so that planning can be done. If there's only like an hour or two a day that, say, a transformer is overloaded, and the BESS can be there lending a helping hand, that's being used for asset deferment. Lastly is grid stability, or at least lastly from what we typically see. This is VAR support, frequency regulation, and capacity firming. BESS standalone or coupled with solar or wind? Good question, and the answer is all of the above. Because of many use cases we just talked about, BESS could easily be a standalone project, and it has many times. Coupling the BESS with solar and wind, though, makes perfect sense. The sun doesn't always shine when you want it to, and the wind doesn't always blow when you need it to. Therefore, when you have the abundance of wind or solar, you charge, and when the opposite is true, you discharge. We're seeing many projects where solar and wind have been already installed or planning to be. Wants to slide again, at least on my screen. We're planning to be, and then coupled with a BESS. Speaking of coupling, BESS can be coupled with solar and wind a couple ways. These are either AC coupled or DC coupled. There's advantages of both, but we'll probably save that topic for maybe a future webinar. Let's go to some typical design considerations. BESS projects are not unique to most any other project where equipment needs foundations. So either concrete options or helical pier options are often considered. We are looking at some options to use in like an engineered subbase that's not concrete to save construction time and cost, but still provide the stability that's needed. There's definitely some challenges there with the containers, so traditional foundations are typically used. More times than not, equipment is connected together with cables, often underground. In some areas where there's a lot of power flowing, where like maybe multiple sets of cables would be needed due to the high current. A bust or solid copper bar is preferred to make those connections. To make these areas safe, grounding and lightning are typically considered, where study is performed and design is developed and installed. We use IEEE and NFPA pretty regularly for those studies and design. And then this permitting bullet is really focused around authority having jurisdiction. Depending on where the BESS is physically, the AHJ may be a significant factor or not. This includes any permits that may be needed, specific county or city or township requests, and definitely the local fire department's desires. These requirements can be very different across the United States, and as all these entities learn about BESSes, the requirements are likely to change. And then the schedule. Every project has one, but BESS often have an added complexity with the battery racks and containers. These often come from overseas and are not off-the-shelf, pre-designed, ready to ship components, so detailed vendor drawings are not readily available. Also, most of these projects, from what we are seeing, are engineer, procure, construct contracts, where schedule is agreed to early in the project. Even though the slide lost on my end, I'm going to just keep talking. Engineering design need to happen early before all information is known, so equipment can be procured. In addition, we often see communication breakdowns with drawing changes occur in manufacturing, and it doesn't make it back to us as timely as we'd like it to. It happens pretty often, so you have to plan for it. I'm not sure what's going on if it's just my screen, but I don't have the slide show up anymore.
Oh, we can't see the slide anymore. So I
Okay.
think it's technical difficulties.
Well, I'm going to assume Dell's going to get that figured out.
So while we wait for him to do that, I can throw you a question that's out there that you can address before we go on to your next slide. And that is fire suppression requirements. What fire suppression requirements does a BESS require? There have been fire reports of cascading thermal runaway issues with BESS. What additional fire protection systems have been developed to prevent BESS fires?
So I would say yes, and it's a developing topic. Some are flooding containers with water. Lithium ion tamer is being utilized, hydrogen detection. Really, it's been preferential to each project, but as more and more of these go in, people are learning more and trying to be more safe. And yes, there are some requirements, and kind of depends on whether we're talking about commercial or utility scale. Those requirements may or may not, have to be used. But definitely the answer is yes. We need those things. You just have to determine what is needed in that area. Okay, lessons. I'm going to jump to that. I hope that answered the question. I kind of jumped around a little bit, but lessons learned. Number one, standard equipment. It's really not all that standard, and we don't always get true what we consider shop drawings. So the equipment vendors often send like installation manuals that are similar to what you get for your car. It covers like every option, every upgrade, and many times different model years. So it's kind of hard to tell what you're getting. Ask lots of questions and have to figure it out over the course of the project. Number two, equipment openings are often bottom fed and very small. So the electric code determines how many conductors and the size of conduits we need, and they don't always fit so well, and at least they do fit on paper, but it's hard to do it in the field because it's very tight. And then mentioned the schedule earlier. Schedules are often adjusted for any project, and BESS projects are no different. Consideration here is that BESS project may appear to be pretty straightforward as I kind of walked around the major piece of equipment. There's a lot of little details to consider. And with the EPC contracts mentioned earlier, there can be penalties for missing an in-service date. And then number four, bullet four there, safety and education. This is key for any project, but what makes BESS different is that the batteries are never completely dead. They may be at their lowest possible state of charge, but they still have enough energy to create like significant safety risks. So care has to be taken at all times, and educating everyone involved is very, very important. And that is it for me. So I'd like to introduce Ian Hutt.
All right, thank you, Jack. Appreciate that. So my name is Ian Hutt. I lead the electrical studies group at Commonwealth, and I've been working pretty heavily on the battery energy storage systems. And I want to talk a little bit about common studies that we have performed on electrical systems related to batteries. So there's four major studies that we tend to look at. We look at the AC and the DC short circuit studies when it comes to BESS applications. And what we're really trying to find out with short circuit studies is making sure that the equipment is rated for the fault currents that are expected for a battery. And on the AC side, it's important. On the DC side, we're seeing some challenges there, and we'll talk about that here shortly. We also do load flow studies, and load flow studies are really focused on looking at two major things. We wanted to make sure that the cable sizing and the equipment are appropriate for the ratings of the equipment. So for example, you don't want too small of a cable to handle the normal maximum flows for one of the battery applications. And it's important to look at different conditions like low voltage. It may drive up current a little bit. We also look at voltage drop. So we want to make sure that the requirements from from the buyer is going to be met. So if you have too long of a cable, you may have excessive voltage drop, and we may need to do some upsizing because of that. Another common study is we'll look at protected device coordination. So what that means is we want to make sure that the protective device closest to the fault operates, leaving the most amount of equipment up and operational. So that's important. It kind of a way to visualize that is if you think about your breakers in your house and your panel in your house. If you had a fault on one, like say your outside outlet, you don't want to lose the whole house. You just want to lose the outside outlet. So that's kind of what protective device coordination is really focused on. We also look at the arc flash at the site. It's very important that we try to keep our workers safe when they're working around energized equipment. So we'll look at both the AC and the DC arc flash for worst case conditions. And we're really trying to make sure that when workers are in and around and working on energized equipment, that they have the appropriate protective equipment on for the category of arc flash ratings that exist. So talking about some challenges, these are some of the current challenges that we experience when we're doing electrical studies for our battery energy storage systems. The first challenge is talking about very high DC fault currents. So what we see is to be able to get the energy density required for lithium ion batteries, we're kind of limited on our voltage. So on the DC side, we're limited somewhere between 800 and 1500 volts. And that's really based on the inverter manufacturers themselves. So the inverters on the DC side don't want to allow too high a voltage because it requires the inverters to get larger and more expensive, mostly because the added insulation required inside the equipment. So what we see is we have kind of typical ranges that we see the inverters manufacturers really targeting for DC maximum voltages. The problem with that, if we're limited to 1500 volts and we're talking about getting to megawatt size long duration batteries, the only way to get the energy density required for this long duration battery is to add more and more batteries in parallel. And what happens when you do that is when you have short circuit conditions, these lithium ion batteries are very, very low impedance, and they can result in very, very high fault currents. And the only thing that really protects us or even limits us a little bit on that is the collector system cabling, which is also designed to be very, very short. So we'll talk about that in more detail as we proceed here. We're also seeing on the high DC fault currents, the central inverter designs are kind of what's driving this issue. And it's the preferred methodology right now, mostly because central inverter designs allow us to do things like microgrid forming. Another current challenge that we're working with is dealing with high arc flash values at the BESS GSU transformers. Now, these are the step-up transformers that go from the inverter to the medium voltage network or distribution connected microgrid based battery energy storage systems. I guess it's microgrid or grid connected. And what we'll find is with the distribution system strength connecting through these very large transformers, generally relatively close to distribution substations, that we can see very, very high fault currents on the low side of these AC transformers. And the other problem is protective devices have a very hard time detecting these faults because they have to look through the transformer and they're subject to the turns ratio of these transformers. So if you have a medium voltage network somewhere between say 15 kV and 35 kV, and you're transforming it down to a typical AC voltage level, somewhere between 400 volts and 600 volts AC, there's a lot of turns ratio there. So the amount of current seen by the protective devices is very, very small. So typically where you expect a fuse to operate very quickly, they operate slowly, causing very large arc flash. Another challenge that we're seeing on battery energy storage is dealing with microgrid grounding. So when we use a battery energy storage system and a distribution system, we have the opportunity to form a microgrid. And I'm going to define microgrid as a separate grid from the typical utility connection. So we're going to, after we lose the utility connection, we're going to form our own grid with the battery and the inverters from the batteries themselves. When we do this, it provides some challenges. So normally when we have a lot of system inertia and system strength, when we're in this IBR-based microgrid, we lose a lot of that. So it can be very challenging sometimes to provide effective grounding and also protection settings that can detect and clear faults. So I want to talk about the high DC fault currents here for a second, and that's going to be the focus of our talk today. I'm going to show an example case here. This example case is a battery energy storage system that Commonwealth helped assist design in West Texas. And this battery is a very large utility application, although I will state that we're building bigger and bigger batteries every day. This is a 40 megawatt application in the west side of Texas. And this arrangement consisted of 20 different inverters that are all rated at 2.475 megawatts each. And the target capacity of this battery energy storage system was 2 hours. And what that means is we're taking a central inverter design where we're taking a very large inverter and putting a lot of batteries behind that to be able to get to that 2.475 megawatt output range. And we want to be able to do that for the energy density requirement of 2 hours. But what we're seeing is when we put enough batteries in parallel and in series to give that energy density at the appropriate voltage ratings of the inverter, in this case it was maximum at 1500 volts DC, we're seeing very high fault currents. So on this next slide, I have an example. This is coming out of our ETAP software program. This is a steady state program that looks at the potential maximum DC fault currents. And what we're finding is we're seeing very, very high DC fault currents. And just to give some perspective, if we talk about some of the most challenging AC fault currents in the entire Eastern interconnection, generally between 65,000 amps and 80,000 amps is considered extremely, extremely high fault currents. And a very, very high magnitude. It's very difficult to find equipment that can handle a fault of this magnitude. And what we're seeing for our DC system, we're seeing DC fault currents that are up to 2 times that number. So at our inverter bus, we're seeing fault currents of up to 172,000 amps. Also, at the inverter bus, you have some beefier equipment, some thicker and more fault-capable handling fuses. But when we get down to the string fuses, which are on top of the battery stacks themselves, this equipment isn't quite so built. So what we find is we have challenges in trying to make sure that the equipment is rated to handle these very, very high fault currents. So as a rule, we're seeing on the DC side, generally 50,000 amps is the typical equipment maximum for handling fault currents. And what we can see here is we have fault currents at the battery that are high, upwards of around just under 100,000 amps. And we see that the actual containers that these fuses live in will have to see fault currents of around 120,000 amps. So how do we deal with that? If the equipment is below its rating, how do we find a way to move forward? Well, the first issue would be to work with the equipment manufacturers to have them really look at testing their equipment to see if it can handle these high fault currents. Sometimes that's not even possible. To even generate these fault currents in a lab can be very, very challenging, even with our current testing equipment. So another method that we have is the use of current limiting fuses. So current limiting fuses are very, very understood when it comes to AC systems. The time constant of AC systems is very well understood. We can measure this. We can apply current limiting fuses to most 60 hertz systems relatively easily with typical time current curves provided by the fuse manufacturers. However, that doesn't apply to DC systems, especially when we get into battery energy storage. So for battery energy storage, the time constant of the DC circuit is entirely dependent of the RLC of the DC collector system. And it's all one big circuit with all the different series batteries as sources. In this case, we had 52 sources feeding into this inverter. So it can be a very challenging and detailed operation to look at this. So here's what happens is basically when we have a fault, the fault current doesn't necessarily go from zero fault current to maximum fault current instantaneously. It happens over a period of time. There's a DC rise. So what we have to do is we have to look at the race between these current limiting fuses and the DC rise. Will the fuse burn before the maximum fault current is reached, or will the maximum fault current be reached before the fuse burns? And that's something that we have to investigate. And we have an example of how we looked at it using some advanced engineering software. So here what we're looking at is we're looking at the AS squared of the fuse, which is telling us how fast this fuse will have a melt and a total melt time before the fuse will completely clear the fault, and what the maximum fault current that will be reached during this. So for this particular instance, we looked at it and the fuse is much faster than the DC rise of the circuit. And we can see that on our bottom part of our graph here, that although we have a potential of almost 100,000 amps available, we have 7,800 amps will be the actual realized fault current, which is much less than the 50,000 amp fuse ratings that we have for this application. So here's kind of an example of what I'm talking about. So what we're showing here, this is credit busman fuses. This is a graph for a typical AC application of a current limiting fuse. And what we're talking about is our fuse clearing time, our TC in the graph, is basically showing how much time is going to pass before that fuse totally clears the fault. Now, generally, when we have current limiting fuses, they're based on AC time constants. Those are usually in the 10 millisecond ranges. However, our best DC fault current rise is very, very fast, generally in the order of 0.1 to 1 millisecond. So 1 to 2 orders of magnitude faster than our typical AC systems. So that's the main challenge that we have, is making sure that we understand, what this race is. And typically in AC systems, that these current limiting fuses will be much faster than the AC rise. Therefore, the current limiting fuse will be very, very effective. On DC systems, we can't say that without further study. So I wanted to mention that although I don't have any connection to these manufacturers, we've done a lot of research, and through our experience, we found a number of protective device manufacturers that have built equipment particularly designed to deal with these high DC fault currents and with the upcoming battery energy storage market. So what we're finding with SEBA, that we have some combiner fuses. These are the fuses that are very near the inverter that can handle fault currents upwards of 170,000 amps. We're also seeing that Fuse also has string fuses. These are the fuses that go on top of the battery stacks themselves with very high ratings as well, up to 250,000 amps. And these are tested ratings by the manufacturers. Merson has a 100,000 amp string fuse rating in their Prosistor series, and Busman has a line of DC fuses that are up to 90,000 amps. So there is some equipment that can deal with these high fault currents, but as you can see, with some of the fault currents we saw from our example, that even the devices with very high fault current ratings are very near what we're experiencing in the field. So again, just another example of kind of what we're talking about with these current limiting fuses is that we're really looking at this race. So how steep that curve is on how fast that the fault current rises is really what we're tracking. And you can see with the red line that I imposed on this graph that the DC systems can be much, much faster than the AC systems. And if that DC rise is fast enough, it may rise before the current limiting fuse can operate. And what we saw with our last example, we were coming in somewhere between 0.8 milliseconds, but we've seen applications that are much faster than that. So just to summarize, how can we help our customers with this problem? Well, the first thing that we always try to do is look for and recommend devices that are rated for what we anticipate the DC fault currents to be. And this is going to become a growing problem. So a lot of the batteries that we've worked on so far have been relatively short duration batteries. As we go to what I consider the end all of batteries, we want to get to like the mythical 12-hour battery. This 12-hour battery would be perfect. So we know that the sun is generally shining 12 hours a day. I understand that there's summer and winter differences, but it'll get us through the night. So we want to make sure you have batteries that can soak up all the renewables during the day or when they're available and then discharge during the night. So we want to try to get longer and longer energy densities. Now what we're going to find is the more batteries you put behind an inverter, the more this is going to become a challenge. So we want to work with our manufacturers very, very early. We want to come up with preliminary studies that look at what we anticipate the DC fault currents to be, and then try to find equipment early to be able to handle these very large DC fault currents. Alternatively, if we find that equipment ratings are lacking in these areas, then we can look at further study. By going to detailed transient analysis, it allows us to look at the current limiting function of these current limiting fuses and whether they're really going to be effective for our particular application. And I will mention that every single site is slightly different. So as collector systems change based on layouts and designs are going to go to Jack's point, batteries can be put anywhere. Sometimes you're going to put batteries in very small spaces where you have a little bit of extra space, and the layout's going to have to change and be adjusted to accommodate those applications. We're going to find that every time we're in a non-standard layout, that all these studies have to be done again. All right, well, thank you very much. And I'd like to pass the mic over to Colleen. And if there's any additional questions, I'm here to be able to handle those now.
All right, I have one more that's on the docket before we pass to Kelly. So the next question is, what are some considerations to keep in mind when adding a BESS to an existing solar PV site? AC versus DC coupling or high voltage versus low voltage coupling?
Okay, sure. So it makes sense if we want to try to get our battery energy storage very close to the renewables. There's a lot of tax credits out there that are tied to this too, where if you can prove that you're charging your batteries 100% on renewables, you get additional tax benefits. So there's different advantages one way or the other. If we talk about having a DC coupled battery system, you're going to have a DC to DC inverter in play here. And that DC to DC inverter is going to be able to see less losses because you're only going through one inverter to move power from a renewable DC source, for example, a type 4 solar or type 4 wind, to your battery system. I will state though, when we use DC coupling, although it's by evidence very much the most direct way to charge a battery directly off renewables, you do have the challenge of there's really not that many applications there, and you have very limited supply of inverter manufacturers that'll provide quality equipment to handle this. What we're seeing in the industry right now is more and more AC coupled systems. Now, for an AC coupled system to make the argument that they're charging directly off renewables can be maybe a bit more challenging and will require metering to be able to do so, but it is possible through control systems to do this. What we find is you have more available inverter technology in the market, and what I'm seeing is the vast majority of inverter manufacturers are focused on AC coupled systems. So you're going to have the latest and greatest equipment. And what we're seeing is very, very fast-paced changes in technology on these inverters right now. So even the firmware updates that are happening, we're seeing updates every 2 to 3 months that are significant technology changes, making these inverters better and better. So I think it's important that we kind of, as we go forward, that using the AC coupled method is going to be maybe the way to go. And we'll see that with the upgrades in the inverter technology.
All right, thank you very much, Ian.
Mhm.
And we can turn it over to Colleen now.
Hello. Hello, everyone. I think it's working now. Thank you, Ian.
Yeah, thank you.
Let's pause for a moment and take stock of what we've learned here today so far. We've talked about the definition of a battery energy storage system, general system design considerations, current challenges, and some DC protective device considerations. But what about the rest of the picture? Look out there. We see in our picture that batteries can actually connect to the grid, either at the transmission level or the distribution level. So specifically, let's talk about what happens when we connect community-based generation resources, like batteries, to the power grid on the distribution side. So for battery energy storage system design and integration, what are some interconnection design considerations? What are some AC distribution grid protection considerations that are unique to DERs, to things like batteries when we connect to our homes and our communities directly to the distribution grid? What things have changed compared to traditional massive generating technologies that hook to the transmission grid? The answer lies in interconnection considerations. There's a guide, IEEE 1547, that is a standard for interconnection when we are hooking onto the distribution side in a distributed energy capacity. This guide focuses on maintaining grid reliability, specifically as it relates to frequency, active power, and voltage stability. But what do we mean by voltage stability? Who among us has ever seen their lights flicker or dim when the air conditioner turns on? This is an example of voltage momentarily changing, but still staying within an acceptable range. Eventually, the lights come back to their typical amount of shine, and we don't have blackouts on the rest of the grid when we turn our air conditioner on, usually. So IEEE 1547 is a standard that does not describe how to operate battery systems. It does not educate us on exactly how to design those systems, But what it does is specify functional requirements that DER systems, like batteries in a community connection, have to be required to do, the capabilities these systems have to have if they're going to interconnect to the distribution grid. Topics include reactive power and active power, voltage ride-through requirements, voltage trip requirements, frequency. We're not going to go too deep into those details today because we only have a few minutes left in our session, but we are going to take a look at an example of how to interpret this standard. Our goal is to be aware of it as we move forward in our designs for battery systems. So here we have a poll question. Consider that you are an electrical power system operator with a community-based BESS connecting to the distribution grid. If the voltage is coming up on about 113% of what you would expect the value to be, what would you do? So in this case, it's not a rhetorical question. You should see a poll question on your screen. Go ahead and tell us, what would you do? Because of IEEE 1547, we have the ability to choose. So we see here about 65% of us think that 113% of voltage is too high, and we'd want to trip out and remove the batteries from the conversation. But 35% of us think, in our part of the power grid, we want to ride through. We want to see what these batteries can do. Maybe they can help stabilize that voltage somehow. So it's because of IEEE 1547, we as the operators in this example would have the ability to make that decision on what's best for our local region, what's best for our local distribution grid. So let's take a deeper look at our IEEE 1547 example. And here we're talking about voltage control. On the right, we see a chart from the standard that's talking about trip. That means that we are removing our battery system from the distribution network. On the left, we see a chart that's talking about ride through. That would be cases where we are keeping the batteries connected, even if things don't seem to be staying exactly 100% on the voltage where we normally would expect it to be. Previously, IEEE 1547 had a shall trip requirement for most abnormal conditions. That was the 2003 version of that standard. But in the intervening years, the philosophy has changed. So now in the latest standard by IEEE 1547, there are some cases where voltage ride through capability. So the batteries must be capable of riding through no matter what. And there are other times where they have to be capable of regulating voltage. But much of that is on the operator to determine exactly where those ranges will fall. So for our example, we talked about 1.13 per unit, or 113% of our anticipated voltage. So if we zoom in on our slides, as we've seen here, on the right, nope, we're good, one slide back. Yep, on the graph on the right, we see that 113 or 1.13 is considered an overvoltage condition. And there's a recommended default value saying that around 1.1 or 110%, if we're going to de-energize part of our system, we'd have to do that in 2 seconds. But continuing to the right of the chart, we see there's actually a range of allowable values and a range of clearing time that we as the operators could have influence on. And then in the lower left corner, we see with our trip chart that there is a range where there's a permissive operation. And if we're going to be riding through, the battery system has to be capable of riding through for at least 1 second. So this is really informing the battery system engineers on what the batteries could be asked to do when they are grid connected. And it also tells the operators what the allowable ranges are. So there's another way we can look at this in a graphical representation. And if we look at our slice of where approximately 1.13 per unit is on this graph, at a minimum, we can recognize there's 3 colors on the graph. So this represents our options of permissive operation, ride through, or tripping throughout various timelines. So from this, we see there's really no correct answer to our poll question. So we're all winners today. Instead, the correctness of the answer depends on the reliability needs of our distribution system as determined by operators. A battery system, which we could think of as including the inverter to get us onto the AC grid, a controller, things like that. And all DERs, in fact, that are interconnecting need to be designed to accommodate this. We also have a similar consideration for frequency in IEEE 1547. So here we see yet another chart where we have lots of colors and different options to trip or not to trip. But this is below the level of detail for our discussion today. But it's just to give you an idea of how IEEE 1547 is serving as a standard that could influence our design of our battery systems. So let's say we've interconnected. Congratulations, team. Our battery system was designed to be 1547 compliant. That means we've interconnected to the distribution system through some kind of existing distribution infrastructure. But what else can the system do? What else can our DER, distributed energy resources, our batteries do? What now? What if we want to disconnect from the primary grid and supply our battery power directly to our own community? When would we do this? Well, you may recall Texas earlier this year, February and March, had very cold temperatures where they were disconnected from the primary grid. They were unable to receive the power that was being generated in that primary grid. So this is the type of application where a widespread battery system across a community or across multiple homes in a local area could have provided power to that community. So we see there are cases where this capability is useful. Let's consider if any of the protection considerations change. First, we're going to look at a traditional case where the primary grid is supplying most of the power. Then we're going to consider a futuristic case where the batteries are supplying all of the power in islanded mode. We're going to ask ourselves, how does fault handling change? You see on your screen an example. That's going to be a poll question. So before we launch the poll, if we can take it back, or maybe while the poll's going, I'll just explain what's happening here. Yes, thank you. I'll just explain what's happening in our picture. So as a reminder, in a traditional power system, what we think about is having this large supply of generation that's feeding the transmission grid. That's also known as the bulk electric system. There's lots and lots of power being generated, but by the time it's getting closer and closer to our communities, we might see something like 1,000 amps flowing through a transformer on a typical day, coming into our local distribution network, distribution community. And in our example on the screen, we're tapped into that large transmission and generation system, and a tree falls on one of our distribution lines. One of our wooden telephone poles makes contact with the tree. So that means that current now has a path out of our system and into the ground. How many times of current do you think we will see in this fault or near the tree? That's the question I'd like us to consider here for a moment. So on a normal day, we'd see about 1,000 amps coming off of our transformer. But on a non-typical day, when the tree hits the distribution line, how many amps are we going to see entering that red circle area? Let's go ahead and launch the poll and see what your thoughts are on that. So we could have perhaps less than 1 times the typical amount, less than 1 times our base current. We could have perhaps, you're thinking 1 to 2 times the base current. Maybe that seems reasonable. Perhaps you're thinking we're in the 7 to 11 times range. Or maybe you're thinking it's infinitely huge. Oh, okay. I see we're having some technical difficulties, but just think to yourself what that answer would be. So the correct answer in this case is that we would see roughly 10 times the current. So instead of our 1,000 amps flowing around that area, we might see something like 10,000 amps flowing in there. And that extra current is indirectly coming from those massive generation supplies that are up in that bulk electric system area of our screen. But things are limited by the design of our transformer. So we won't see infinitely huge fault current, but we might see something around 10,000 amps flowing into that red circle. This is a line to ground fault, very common on the power grid. And it's also very common to protect us from that kind of situation by using a fuse. So on that little branch where the red circle is, in a typical distribution system, we might see a fuse that's supposed to melt when the amperage is above 1,000 amps, and hopefully before we reach 10,000. The fuse would melt, it would drop house number 2 off of our grid, off of our circuit, and then power would continue to flow to the other houses coming from that bulk electric system. This is what many of us in the power industry have come to know. But now, looking ahead to the future, we have to ask ourselves, what happens when we have a battery system as the primary supply? What happens when our community-based generation is the primary supply in an islanded mode? So to examine that question, we're going to go to another example for distribution fault protection. So that was our traditional case. Now on the screen, we see the case in islanded mode. In this case, we have little blue rectangles representing batteries supplying power into our community locally. Very cool. We could still have 1,000 amps of current flowing around this area, but it's also possible that our batteries are near their max generating power to supply that 1,000 amps. So they're doing well, but they're almost maxed out on how much power they can be pushing through. If a tree falls in the same spot, circled in red, we might see way less fault current coming into that area. That means we still have a problem. We still have current leaking out of our system. It's inefficient, and it could be unsafe because we're not able to control the flow of current anymore. That means we need to eliminate this problem. We need to clear the fault. We need to isolate that section of the line. But how can a fuse that was there from last week when we were grid connected, sized to look for 10,000 amps, how can that fuse looking for 8,000, 9,000, 10,000 amps know that only 2,000 amps is now a problem? Remember, our base current was around 1,000 amps. So going from 1,000 to 2,000 might not be a significant jump from the perspective of the fuse. So this is the new frontier of the power industry as a result of emerging technologies like inverter-based generation, tapping distribution systems. Regardless, how do we reliably isolate this fault? How can we help our customers with this problem? There is no widespread commercial solution out there on the market right now, but it's something to which we think at Commonwealth we may have the answer. So Commonwealth actually has a patent pending protection algorithm that could address situations like these. So please join us on November 3rd for a discussion about Commonwealth's vision of the grid of the future and how our patent pending microruptor algorithm could be a part of it. With that, turn it back over to Christy for a Q&A.
Thank you. We have had another question on if we would be sending attendees a copy of the presentation, and we don't have a problem doing that. So if you would like to receive it, we can go ahead and send that out. And I will open it up. If you guys have any additional questions, if you want to put them out in the chat, we'll continue to answer them as they come up. So I will give you a couple minutes for you guys to put questions out there. So the first question that we have in is, what is the schedule or duration typically for a BESS project? Jack, can you answer that?
Yeah, I can answer that. So it sort of depends on the scale of the project. If we're talking 1 megawatt versus 100 megawatt, obviously there's a pretty big difference there. But engineering timeline is 3 to 4 months, construction another 3 to 4 months, and then commissioning and turnover. It could be done in a year. Lead time on equipment can be 6 to 8 months. So if you planned a year for like a smaller project, maybe 1 to 10 megawatts, maybe a year and a half for a larger project.
Thank you. Is there anyone else that has any questions out there for us? So I guess as we wrap up, and I'll keep watching for questions to come in while we're doing this, I'm going to launch the last poll, and that is for you guys to be able to provide us input on any future webinar topics that you would be interested in. So if you select this, then it will help us know areas that you're interested in, and we could try to wrap our next future webinars around to whatever the desires of the team, I guess. So as we're collecting votes here. So microgrids and renewable integration are kind of the winners for what to look at in the future protection scheme. So I appreciate that. We will use that for our information as we continue to develop some of these webinars. But if we can go to the next slide, the very next one we have already planned and in process is we will be presenting on Wednesday, November 3rd. Colleen, along with her supervisor, Sebastian, will be presenting on some patent pending fault detection that we have been developing at Commonwealth. So if anybody is interested, if you can please, you can note that in the chat. We will be sending out future email invitations similar to what you guys got for this one, and it will also be on our LinkedIn. But if you reply to the chat with your email address, then we will be sure that you're on the list and get you signed up for the next one. We have one more question that came in before we wrap up, and that is, did you see a big use case for the volt var support using BESS?
Ian, do you think you can take that one?
Ian, can you hear me, or are you unmuted?
This is Colleen. I can chime in for a moment here.
Yeah.
Ian might be having technical difficulties. Yeah, so I will just say, oh.
Sorry, guys. I was muted by Dell there. I was trying to get off the mute. Yeah, so the volt var support, I think, is going to be a big application. And Colleen, I think you were looking to maybe second this. We're seeing this happen right now is kind of the new, like static var compensators was kind of like the way that we were doing it in the past. So this is kind of the new method of dealing with it. So we're seeing a lot of applications for this right now. Matter of fact, there's a couple of projects that we're bidding on in the Northeast that's going to be looking at future and first applications of this technology for this method. The cool thing about this is you really don't need a lot of batteries behind it because you can draw in real power and put out reactive power with these inverters. So kind of a cool application. I think something that's going to really take off here in the future.
Thank you, Ian.
Mm-hmm.
All right, thank you all for attending. We appreciate it. If you have any additional questions, please reach out to us. We'll send out the handouts for those. Thank you for attending. We will send out the handouts to those that have provided their email address. And if you would like, we will also include my contact information in there. So if you have additional questions, please feel free to reach out to me. And again, my name is Christy Vomino, and I'm the Director of Power Generation and Energy. Thank you very much for your time.